Welcome to my channel, the next level topics and contents. In this video, I would like to show an explanatory solution to a CSIR chemical science question that was asked in 2024 December, and exam was held on that date. Okay. So this question is from the topic tunneling. And or you say that this topic is from the tunneling from rectangular barrier. So here this is rectangular barrier. Now, in this question, the incident ray is coming from the x less than 0, that is from negative region, 0, and this is minus infinity, this is plus infinity. So the particle comes from this region, incident from this region, and tunnel through this region, and finally goes to this region. Now, what is region? What is the region? Potential decided the region. Potential decided the region. Here, the whole space of this system is divided into 3 regions: first, second, and third. This graph, this part of graph, horizontal part of graph, decide the region, because here the potential is 0, and after that point, the potential is, after this point, potential is V0. And after this point, 0 to L, the potential is again similar to this region, that is potential is 0. So here there are 3 regions, because this point divided the 2 potentials, that is one side potential is V0 and another side potential is V0 and another side V0. So this is called the barrier. This is the barrier or boundary. So this is the vertical line which is equal to V0, potential is V0, and from minus infinity to 0, the potential is 0. Similarly, from L to infinite, from L to x is equal to L to infinite, the potential is 0 also. But in this region, from x is equal to 0 to L, the potential is V0. That is given in question. Okay, all are in question. So, what the question said? A particle incident from region, this, that is first region, is under a potential barrier with finite height, V0. Okay, the potential of barrier is finite height, and this is equal to, the potential is V0, so called finite height. If potential is infinite, then this is infinite height. That was in particle in box. So that is not here. This is V0. So tunneling takes place and finite width, that is L. So this is constant potential barrier and this is equal to L. That is given in diagram. Okay, 0 to L. When the total energy of the incident particle is less than V naught, and incident particle, that particle approaches from the region 1 and after tunneling goes to third region. In this region, the potential is 0 and throughout the regions, the energy of particle is E, because in tunneling, the energy of particle doesn't change. So energy of particle is E in first, in second, in third, in all regions. But the potentials are changed. So in this region, energy is greater than potential. In this region, energy is less than potential, and in this region, energy is again greater than potential. So there are three regions and all have the different combinations of energy and potential. So first of all, we see that what are the wave functions in these three regions. In the first region, second region, and in third region, we see that the potential is 0 here and energy is E. In this region, the potential is V naught and energy is E. And in third region, the potential is 0 again and energy is E. And relation of these two energy are E greater than V is equal to 0, E less than V naught, and energy is greater than V is equal to 0. So what is the wave function in this region, and in this region? Psi1, Psi2, Psi3. Let's say Psi1 is equal to what, Psi2 equal to what, Psi3 is equal to what. So wave function comes from the Schrodinger wave equation. We know that wave function is the solution of Schrodinger wave equation. So I have to write the Schrodinger wave equation for these three regions separately, and then by solving we get the psi is equal to what. So without solving the Schrodinger wave equation, we are trying to writing the wave functions correctly, and this is the method. First of all, see what is the relation between energy and potential. If energy is greater than potential, then the wave function is imaginary. Or wave function is oscillatory. Okay. And this oscillatory wave function is written by the equation, some constant, you take a e to the power I k1x plus b e to the power minus I k2x. You can take negative sign also, but A and B I have taken, and these are positive or negative. So psi is equal to A e to the power I k1x plus B e to the power minus I k2x. Here, that is also k1. What is k1? This is the wave number, or called propagation wave vector. Propagation vector. So we can write the propagation vector easily. The k1 square is equal to root under 2m into, here energy is greater than potential. So always write the positive number here. So energy minus 0 by h direct square. This is the k. So k is always written in this way, that is 2m by h direct square, that is constant. And what is the relation between energy and potential? So first of all, I have to take the higher value and then the lower value. So here energy is higher than the potential, so E minus 0. This is always positive. So K1 is equal to this much. Hence, we see that in first region, the wave function is oscillatory, and this is equal to A e to the power I k1x plus B e to the power minus I k1x. Similarly, in third region also, the potential is 0 and energy is greater than the potential V. So in this region also, the solution of Schrodinger wave equation gives the oscillatory function, and this is equal to a only coefficient change here. So f e to the power I, k1 is similar because combination is similar here. So you can write 3x plus g e to the power minus I k3x, and here you show that k3 is equal to k1. Okay. Now, for the second region, what will be the wave function for the second region? The second region, we see that particle passes through this line. So the energy is less than the potential here. This is the V naught. So if energy is less than potential, then wave function is decaying function. Decaying function. Always. If energy is less than potential, then the wave function, that is the solution of Schrodinger wave equation, gives decaying function. And this is written as psi is equal to, take some constant, that is C and e to the power k2x, and plus, because this is decaying function, so we cannot write I here, and C e to the power k2x plus D e to the power minus k2x. These are the wave functions for these different regions. Okay, up to this, we have seen that in the first region, the wave function is psi is equal to A e to the power I k1x plus B e to the power minus I k1x. That is in first region. Okay, you say this is first region. In second region, the wave function is c e to the power k2x plus d e to the power k2x. And in third region, the wave function is f e to the power I k3x plus g e to the power minus I k3x. Okay. Since this is oscillatory function and this is the region where particle incident for the tunneling. So in this region, both physically, both incident wave and reflected wave are possible. Okay. Which one is incident wave and which one is reflected wave? That we find out by the momentum operator. Because a e to the power I k1x, when we apply the momentum operator, then this gives the k1h direct and a e to the power I k1x. So here the positive momentum signifies that this is incident wave. This is the incident wave. Incident wave. And this is positive. Now, for this e to the power minus I k1x, if we apply the momentum operator, then this gives minus k1h direct and b e to the power minus I k1x. So here the momentum is negative and this indicates that the direction is opposite to the first and incident wave. And so this is the reflected wave and having magnitude same, but direction is opposite. So we see that this part, a e to the power I k1x is incident wave here and this is reflected wave here. And by combining both, the wave function is oscillatory. Okay. In the first region, the wave function is oscillatory here. Now, and both are possible here. Physically, incident and reflected, because this is the boundary, so reflection is possible here. Now, in second region, the functions are decaying, but the region lies from 0 to L. Any one point that is not the infinite. So both the function lies here. If any one point goes to infinity, then we have to select only finite value. We know that wave functions are finite. So in this region, both the functions give finite value, and so in second region, both function combinedly gives the decaying function. So here, up to this second region, we have seen that this is decaying function. Okay. Now, in third region, we have two functions. That is one having the momentum positive, and another having the momentum negative, because this gives the negative momentum, that is minus k3h direct, similar to this region. So here the negative momentum is not possible, physically not possible, because there is no boundary here. So because there is no boundary here. So only this function lies in the third region. So we have seen that in the first region, wave function is oscillatory. In the second region, wave function is decaying. And in third region, the wave function is also oscillatory. But question asking for the mod psi square. Okay, not for psi. Wave function question is for the probability density, not for the wave function. Okay, you see here, the question is the correct plot of the probability density. Okay, mod psi square. So mod psi square in the first region is similar, second region is similar, but in third region, the wave function only f e to the power ik3x remaining part of this third function, that is a negative value of momentum, that function which gives negative value of momentum, that is discarded here. So only the positive momentum values function is lies here. Hence psi star psi, because I have to calculate the mod psi square, and this gives, for third region, this gives f square, and this is equal to e to the power minus ik3x into e to the power ik3x, and this is equal to 1. And so the mod psi square is only f square, and hence this becomes the straight line from constants. So the correct expression, so the correct diagram is that this is the oscillatory, this is decaying, and now this becomes the straight line, because here this is not the function of x here, not a function of x. Okay, so our answer is, so we see that our answer is second, that is correct here. Thanks for watching the video. Thank you.